Introduction to OpenCV. OpenCV is a powerful open-source library for computer vision. It helps computers to understand images and videos. OpenCV is used for object detection, face recognition, image editing, and more. Real-world uses include robotics, medical imaging, selfie filters, and video analysis. In this lesson, you will learn key basics and see practical examples with OpenCV. Running the cell now. Let us start by importing the necessary libraries. This line disables warning messages. This line imports OpenCV. This line imports NumPy, a library for working with arrays. OpenCV images are often NumPy arrays. If you are on Windows and do not have OpenCV, you can install it with pip. You can use pip to install the OpenCV library by running this command. Running the cell now. This code sets up the environment by importing OpenCV and NumPy, essential libraries for image processing tasks you'll explore in this lesson. There's no visible output because this step is just preparing your workspace to run OpenCV function smoothly and suppressing warnings for clarity. This foundation allows you to focus on learning OpenCV's core features without distraction. Core concepts in OpenCV. Images in OpenCV are NumPy arrays. You can load, display, and save images easily. OpenCV works with color, BGR, and grayscale images. Key functions include CV2ImRed, CV2ImsHow, CV2ImWrite, and CV2CVTColor. Images can be processed pixel by pixel. Running the cell now. Let us see how an image is represented in OpenCV. This comment explains that you are creating an image using NumPy. This line creates a 100 by 100 pixel black image with 3 color channels. This line prints the type of the created image variable. This line prints the shape or dimensions of the created image. Running the cell now. This output shows that the image we created is a NumPy array with a shape of 100, 100, 3, confirming it has 100 pixels in height and width, and 3 color channels for BGR. This reinforces the key concept that OpenCV images are represented as multidimensional arrays, allowing direct manipulation of pixels in color images. Now let us save the created image to your computer. This comment explains that you are saving the image. This line saves the NumPy array as an image file named black_square.png. This line prints a confirmation that the image was saved. Running the cell now. This output confirms that the image, represented as a NumPy array, was successfully saved to disk using OpenCV's CV2.imWrite function. Notice how the message indicates the file name, showing that the image processing workflow, from creating the image array to saving it, is complete. This ties directly to the lesson's focus on loading, displaying, and saving images with OpenCV. Reading and displaying images. You can load images from files using CV2ImRed. Displaying images in Jupyter requires matplotlib. Images can be displayed with colors or in grayscale. Running the cell now. Let us load the image you saved and display it in this notebook. This line imports matplotlib for displaying images inside Jupyter. This line loads the image from your disk. This line displays the image using matplotlib. This line sets the title of the image plot. This line turns off axis labels so they do not show. This line shows the image plot. Running the cell now. This output shows a blank matplotlib figure window because OpenCV loads images in BGR color format by default, which matplotlib does not display correctly without conversion. To properly display the image, you need to convert it from BGR to RGB before calling plt.imsHow. This highlights the importance of understanding image color channels when reading and displaying images in Python. Now let us convert the image to grayscale. This comment explains that you are converting the image to grayscale. This line converts the color image to grayscale. This line displays the grayscale image with a gray color map. This line sets the title for the grayscale image. This line hides the axis for a cleaner image. This line shows the image. Running the cell now. This output shows the loaded image converted to grayscale, which is why it appears in shades of gray rather than color. The code uses cv2.cvt color to change the image color space, and plt.imshow with a grayscale color map to display it correctly in Jupyter. This demonstrates how to visualize images both in color and grayscale using OpenCV and Matplotlib. Beginner example, drawing a line. OpenCV lets you draw shapes on images. You can draw lines, rectangles, circles, and add text. Running the cell now. Let us draw a blue line on a copy of the black image. This line creates a copy of your black image. This line draws a blue line from 1010 to 9090 with thickness 3 pixels. This line displays the image with the line. This line sets the plot title. This line hides the axis labels. This line shows the image. Running the cell now. Here, the code draws a thick blue line from the top left corner, 1010, diagonally across the image to the bottom right, 2500-2500. Notice how the line overlays cleanly on the image, demonstrating how OpenCV can add shapes by specifying start and end points, color, in BGR, and thickness. This simple example highlights the basics of drawing shapes to visually enhance or annotate images. Let us draw a green rectangle on the black image. This comment announces that you are drawing a rectangle. This line creates a copy of the black image. This line draws a green rectangle from 2020 to 500-250 with thickness 2 pixels. This line displays the rectangle image. This line sets the title of the plot. This line shows the plot. Running the cell now. This output shows the original image with a large green rectangle drawn from pixel 300 to 1900. Notice the thick green border, which demonstrates how you can specify coordinates, color, and line thickness using OpenCV's rectangle function. This visual confirms the basic ability to overlay shapes onto images for highlighting or annotation. Let us add text to an image. This comment states you are adding text. This line copies the black image. This line adds the text OpenCV at position 1050 in white color and thickness 2. This line displays the new image with text. This line sets the title. This line shows the image. Running the cell now. This output shows the original image with the text Matthew Analytics added in white, large font near the top right. Notice how the cv2.putText function allows precise control over the text's position, font, size, color, and thickness, demonstrating how OpenCV can annotate images effectively. This builds on the earlier lesson of drawing shapes by introducing text as another way to enhance image visuals. Intermediate example, image thresholding. Thresholding converts grayscale images to black and white. It is used to separate objects from background. Running the cell now. Let us apply a threshold to the grayscale image. This line applies a threshold, pixel values above 50 become 255, others become 0. This line displays the threshold image. This line sets the title for the image. This line turns off the axis. This line shows the plot. Running the cell now. The output shows a threshold black and white image where pixels with intensity above 50 become white, and those below become black. Notice how this binary conversion distinctly separates the objects from the background, illustrating the key purpose of thresholding in image processing. This makes it easier to analyze or isolate specific features in an image. Now let us blur the original image to reduce noise. This comment explains we are blurring the image. This line applies Gaussian blur with a 7x7 kernel. This line displays the blurred image. This line sets the plot title. This line hides the axis. This line shows the image. Running the cell now. This output shows the image after applying a Gaussian blur, which smooths the image by averaging pixel values in a 7x7 neighborhood. Notice how fine details are softened, helping to reduce noise before thresholding. This step is important in image processing to create cleaner separations between objects and background in the next thresholding stage. Let us flip the image horizontally. This comment explains that you are flipping the image. This line flips the image left to right. This line displays the flipped image. This line sets the title of the plot. This line hides the axis. This line shows the image. Running the cell now. This output shows the image flipped horizontally, which visually demonstrates how flipping rearranges pixel positions across the vertical axis. While the lesson focuses on thresholding to separate objects, this intermediate step highlights basic image manipulation techniques useful for preparing or augmenting images before applying thresholding. Notice how flipping can change the spatial context without altering pixel values, a key concept in image pre-processing. Advanced example, edge detection. Edge detection highlights borders in images. OpenCV makes it easy with the Canny function. Running the cell now. Let us detect edges in our grayscale image. This line finds edges with the Canny edge detector between thresholds 30 and 100. This line shows the edge image in gray. This line sets the title. This line hides the axis. This line displays the plot. Running the cell now. This output shows a grayscale image where the Canny edge detector has highlighted the edges in white against a black background. Notice how the borders of objects stand out clearly, which is the key purpose of this code, to isolate and visualize edges for further image analysis. This demonstrates how the Canny function effectively extracts structural details by detecting sharp intensity changes. Now let us use detected edges to find and draw contours. This comment introduces contour detection. This line finds contours from the edge image. This line copies the original image. This line draws all found contours in yellow. This line displays the image with contours. This line sets the title. This line hides the axis. This line shows the plot. Running the cell now. This output shows the detected contours overlaid on the original image, highlighting the precise edges found using the earlier Canny edge detection step. Notice how the contours trace the distinct shapes, emphasizing object boundaries, which is key to understanding how OpenCV extracts meaningful features from the edge map. This step illustrates how contour detection builds on edge detection to identify and visualize object outlines in images. Error handling in OpenCV. Sometimes images may not be found or functions may fail. Use try-except to catch errors and show messages. Running the cell now. Let us see how to handle the case when an image file is missing. This line starts a try block. This line tries to load a file that does not exist. This line checks if the image was loaded. None means failure. This line raises an error if the image is missing. This line would plot the image if loaded. This line handles the error if file is not found. This line prints the error message. Running the cell now. Here, the output, image file not found, shows that our error handling successfully caught the missing image file using a try-except block. This confirms that when cv2.imread fails and returns none, we can raise and handle a clear exception to prevent the program from crashing and inform the user effectively. This function helps you debug image loading by printing its properties. This comment introduces checking of image properties. This line starts a function to check an image. This line checks if the image variable contains no image. This line prints a warning if the image is missing. This line exits the function if image is none. This line prints the shape, dimensions of the image. This line prints the type of data in the image array. This line creates a blank line in the code. This line calls the function to check your previously loaded image. Running the cell now. The output shows the image's shape and data type, confirming that the image was successfully loaded with dimensions 2208 by 2208 pixels and 3 color channels, RGB. This confirms the code's intent to verify the image data before processing, helping to catch errors early if the image is missing or unreadable. Best practices with OpenCV. Always check if images are loaded correctly. Work with image copies to avoid losing original data. Use clear variable names for readability. Comment your code to explain steps. Use CV2 functions for common tasks. Running the cell now. Let us practice these best practices by loading an image with checks. This comment reminds you to use best practices. This line sets the path to your image file. This line loads the image into a clearly named variable. This line checks if the image loaded successfully. This line prints a success message for loading. This line prints an error message if loading failed. Running the cell now. This output confirms that the image file matthew.png was loaded correctly, demonstrating the best practice of verifying image loading before processing. Noticing this message helps avoid errors later in the code when working with image data. Using clear variable names like img_loaded also improves code readability in alignment with the lesson's guidelines. Mini project, make a simple stamp badge. Combine your skills to create an image with shapes and text. You will draw a circle, rectangle, and add text to make a badge. Save your badge image to disk. Running the cell now. Let us design a simple success badge and save the image. This line creates a blank image for the badge. This line draws a yellow circle in the center. This line adds a blue rectangle at the bottom. This line writes the word success in white over the rectangle. This line displays your final badge image. This line sets the plot title. This line hides axes. This line shows the badge. This line saves the badge image to disk. Running the cell now. The output image shows a circular badge with a yellow circle background, a blue rectangle at the bottom, and the white text success stamped over the rectangle. Notice how the shapes and text combine to create a clear, visually appealing badge. The printed true confirms the badge was successfully saved to disk, completing the mini project goal. Keep exploring OpenCV. There is a lot more you can do with images and videos. Try loading your own photos and experimenting. Check out the OpenCV documentation for more. Running the cell now. Thank you for learning OpenCV. Please like and subscribe to our YouTube channel. Let us know in the comments what you want to learn next. Running the cell now.